Equilibrium of a particle. Good day, everyone. In this lecture, we will study the equilibrium of a particle, which is one of the fundamental concepts in statics. Equilibrium occurs when all forces acting on a particle are balanced, resulting in no acceleration. Understanding particle equilibrium is essential because it forms the basis for analyzing structures, mechanical systems, and engineering components. Throughout this chapter, we will learn how to represent forces using free body diagrams and apply equilibrium equations to solve engineering problems. Objectives. The objectives of this chapter are straightforward. First, we will learn how to construct a free body diagram, commonly known as an FBD. This diagram helps us isolate a particle and identify all forces acting on it. Second, we will apply the equations of equilibrium to determine unknown forces and verify whether a system is balanced. By the end of this chapter, you should be able to analyze both simple and practical equilibrium problems systematically. Condition for the equilibrium of a particle. A particle is considered to be in equilibrium when it remains at rest or moves with constant velocity. According to Newton's first law, this condition is satisfied when the resultant force acting on the particle is zero. In mathematical form, the sum of all forces must equal zero. This equilibrium condition is both necessary and sufficient. If the net force is zero, acceleration is zero, and the particle remains in equilibrium. This principle serves as the foundation for all equilibrium analyses in statics. Free body diagram, FBD. The free body diagram, or FBD, is one of the most important tools in engineering mechanics. An FBD represents an isolated particle together with all external forces acting on it. Common force sources include springs, cables, and contact surfaces. Springs generate forces according to Hooke's law. Cables carry tension only, and smooth surfaces provide normal forces perpendicular to the surface. When drawing an FBD, always isolate the particle, show every external force clearly, and label known and unknown quantities. A correct FBD is often the key to solving the entire problem correctly. Coplanar force systems, 2D. In a coplanar force system, all forces lie within the same plane, usually the xy plane. For equilibrium, the sum of forces in the x direction and the sum of forces in the y direction must each equal zero. When solving problems, begin with a clear free body diagram. If the direction of an unknown force is uncertain, assume a direction and proceed with the calculations. If the computed result is negative, it simply indicates that the actual force acts opposite to the assumed direction. This approach simplifies the analysis of two-dimensional equilibrium problems. Three-dimensional force systems, 3D. In three-dimensional force systems, forces can act in the x, y, and z directions. Therefore, equilibrium requires that the sums of force components in all three directions be zero. Complex force systems are often expressed using Cartesian vector notation with unit vectors I, j, and k. The recommended procedure is to establish coordinate axes, draw a complete free body diagram, resolve forces into components, and then apply the equilibrium equations. As with two-dimensional problems, a negative answer indicates that the actual direction differs from the assumed direction. Chapter Review Summary. To summarize this chapter, equilibrium occurs when the resultant force acting on a particle is zero. Every problem should begin with a properly constructed free body diagram. For two-dimensional systems, we use the equilibrium equations in the x and y directions. For three-dimensional systems, we extend the analysis to include the z direction. We also reviewed common force elements such as springs, cables, and contact surfaces. Mastering these concepts provides a strong foundation for more advanced topics in statics and mechanics.